Good afternoon to all from the editorial board of BuildUp portal. For the ones who are attending a BuildUp webinar for the first time, welcome. For our returning audience, thank you for renovating your interest. Just a brief explanation of what is BuildUp. BuildUp is a collaborative platform in the field of energy efficiency in buildings. It is continuously updated and it represents one of the key sources of information on the topic of energy efficiency. You can register and become a member of the community. And you can also upload news, events, present a case study, results from projects, and so on. I would like to invite you all to navigate the portal. In the Learn section, you will find all the podcasts of the past webinars, so it is possible to listen to all the previous presentations. At the end of this webinar, the link to the full presentation and the file to the PDF presentation will be made available in this section of the portal. It is a pleasure to host today's 8th webinar of the EPB Standards series entitled Example Calculation with a Set of EPB Standards, Energy Needs Combined with Specific Systems, which is organized in collaboration with the EPB Center and RIVA, Federation of European Heating, Ventilation and Air Conditioning Association. As you can see from the screen, we have scheduled a series of webinars on the topic of EPB standards. Take note about the next webinar, which is taking place on the 8th of December and is entitled Whole Building Calculations from Components to Overall Primary Energy. I would like to invite you all to contribute and participate in this webinar. You can ask questions by typing in the box on the right side of the screen. All questions will be answered at the end after the presentations. So now I would like to present the agenda of today's webinar and introduce the 4 panelists. First, Jaap Hogeling from the Energy Performance of Buildings Project Group and the European Committee for Standardization will do a brief introduction. Then Dick van Dijk, an EPB expert from the EPB Center, will explain coupling of the thermal zone, EN ISO 52016/1 and heat pump systems. Then Gerard Zweifel, EPB expert and Professor Emeritus from the Lucerne University of Applied Sciences and Arts, will discuss the coupling of the thermal zone and ISO 52016/1 and natural ventilation methods. Finally, Laurent Sokal, independent EPB expert, will present some preliminary examples of whole building calculations. So now I leave the floor to Jaap Hogeling and we can start the session. Thank you.
Good day to you. Welcome to our webinar. I will say a few words as introduction to our speakers. My background is chairperson of the CEN-TC 371 and project leader on the development of the set of EPBD standards. The goal of the example calculations is to demonstrate the functionality of how the calculation works with practical cases and the available features to describe energy performance of buildings and their installations. The sensitivity of the calculation procedure demonstrate which impact single data or group of data on the selected calculation results have, and the usability to demonstrate the data input, avoiding unnecessary input complexity, description of practical system configurations, and show useful results. And this all of individual calculation modules and of a whole building calculation procedure. It is about the coordination between the modules. Several modules will be tested together to see the effect of the interrelation between the modules, typically to see the effect of operating conditions, and a collection of modules will be tested by connection of spreadsheets, generating results for particular cases as explained by the different presenters. And as said in the introductions, We will present here specific examples on the energy needs calculation combined with specific systems and a preliminary example of a whole building calculations. Thank you very much, and I wish all success for the next speaker.
So good afternoon to you all. My presentation today will be on the coupling of the thermal zone calculation with the calculation of a heat pump system according to the two standards which you see here in the title. If you want to read more about my background, you can look up this slide later on in the recording, and I'll continue with just explaining that well, this is already the 8th webinar, and so there might be some background information in the previous webinars which you would like to look up or need to fully understand what is presented today. So for instance, on the second webinar, we gave an overview of all the EPB standards, and on the fourth webinar, we explained the difference between hourly and monthly calculation methods. And for instance, on the seventh webinar, the previous webinar, we gave an introduction to the example calculations on which we progress today. So my presentation is actually divided into two parts. The first part is a general part on the coupling between energy needs and the systems. And then the second part of my presentation is specifically on the coupling to heat pump systems. So at the previous webinar, I asked as a first question, well, where to start with the calculation if you look at the set of about 50 EPB standards. And I explained, well, the most important standards if you want to start with the calculation are calculation of the energy needs according to ENISA 5216. So it gives you the energy needs for heating and cooling and the internal temperatures in the building. And then the second core standard is ENISA 52000 Part 1, overarching EPB standards. This standard is about the aggregation of all the energy uses by the different systems, also energy exported to the grid if you have electricity production on site and so on, and very important, conversion of primary energy. But Laurent Sokal will explain more about this part of the calculation further on today. And so this is what I said at the previous webinar. So now at this webinar, I concentrate on the link between the energy needs calculation and one of the system standards, which is the heat pump system standard. So you've probably seen this slide several times before if you are participating in these webinars since some time. I just want to show it again because it is important to realize that the energy needs calculation according to this standard contains both the hourly and the monthly calculation method, and in the spreadsheet that is developed to demonstrate the calculation procedures in the standard, we have both the hourly and the monthly calculation method running in parallel with the same input data. Actually today I will concentrate on the hourly calculation, and if you make the link with the systems, then you are beginning to divert from the monthly calculation method, because then you would, for the monthly calculation method, also introduce some factors that correctly show the interaction with the systems. Again, a slide which I showed at the previous webinar, but again, quite important to realize, is that the tools we are using for these example calculations are spreadsheet tools. These are publicly available at the EPB Center website, or they are in preparation, for instance, updated versions of it. And these are mainly intended to demonstrate and validate each of the standards. And the spreadsheet is not identical with the corresponding standard in the sense that the spreadsheets have some limitations, as I explained last time. And the highest priority for the spreadsheet is that they are technically correct and transparent. Specifically on the transparency, where possible, all the intermediate results are shown. You can trace the calculations step by step, and also step by step, for each step, references are given to the corresponding clause of the formula in the standard, and that makes it quite important tools for the demonstration and validation of the standards. At the cost of user-friendliness and performance, unfortunately, and therefore they are not intended for daily practice to assess the energy performance of the building. Also shown at the previous webinar is the type of output of the 52016 part 1. And this time I concentrate on the calculation of system-specific loads and needs. That's the interaction with the systems. And the output is then the hourly heating and cooling load and the hourly indoor temperatures. Well, how is the coupling working between the energy needs and the system? Here a general picture. So you have the calculation according to EN ISO 5216 part 1, hourly calculation. And from that you get data from the energy needs from this calculation to the system. So that's input to the spreadsheet on the system. That here the calculation is done to get the performance of the system, and these data are then fed in as an input to the spreadsheet on the calculation of energy needs. So this is done by an hourly time step, and that sounds actually more simple than it is, because there are some complications in the whole calculation. For instance, if you look at the way that EN ISO 5216 calculates the energy needs for heating and cooling, it does it by 2 or 3 steps. So first step is, well, it tries for each time step, so to say. For each time step, it starts with the calculation of the thermal balance without heating or cooling, and then you will get the operative temperature, and it then is checked whether this operative temperature is within the set point for the heating and cooling. If that's the case, then you're done for this time step. You can go on for the next time step. If this is not the case, if the temperature is too high, then you need cooling. If it's too low, you need heating. And then the next step is a guess of this heating and cooling system actually, or need that is required. Actually, it's just simply taking a large value of the heating or the cooling needs. It runs for the second time the thermal balance, and then you get again the temperature belonging to that high heating or cooling need. And from these two calculations, without heating and cooling and with this high heating or cooling, you can interpolate the estimated heating or cooling need. And having said that, this is in case of an unlimited heating supply, but in case you have a system specific calculation, you check whether the system can deliver this heat. So depending on the available heat from the system, you will have this unlimited need for this time step, or you have a reduced energy need for the time step. In any case, with the given heating or cooling needs, you have to do a third run, because if you changed the heating needs, then you also change the temperatures in the building, not only the air temperature, but also the temperature of the fabric of the building, all the constructions. So you do a third run, and then you're done. You have the energy needs and you have the temperatures for the building. Well, if there are some dynamic effects introduced within the time step, then you may need to check again whether it's really whether the interpolation done here really gives you the operative temperature within the boundaries of the set points for heating and cooling. If that's not the case, you do the interpolation again, and you can do that of course with many iterations, but here in the spreadsheet we've limited it to 5 iterations, and then you're done. Maximum 5, minimum is 1 if you have no heating or cooling needs. So where does the connection to the systems come in? Well, actually they come in here at each loop. You get the data from the energy need calculation, you run the system spreadsheet, and you get output from system, so the performance of the system, which includes the available system power, and you do the calculation accordingly. So that was the generic approach. Now more concretely, specifically for the heat pump system. As you know, the EPB standards are built up like a modular system. And if we look at the heating system, we have 3 modules here shown. That's generation subsystem, illustrated here, the distribution subsystem, and the emission subsystem. And you could also add the storage subsystem, of course. So for the connection of the heat pump, you have the heat pump here as a generator, and you have the energy need here who extract the heat from the emission subsystem. And as you notice, there are 2 steps in between, is distribution and emission. Well, the distribution system is for now neglected, and with respect to the emission system, what cannot be ignored is that for higher energy needs, you need higher temperature of the emission system to be able to supply the higher energy needs. So you see here the heating curve, and so this heating curve is introduced in between the calculation of the energy needs and the heat pump system. So this means that now converting the generic picture to a specific picture for what's happening between these two spreadsheets. So for each time step from the energy need calculation, the is fed as an input to the heat pump calculation is the energy need for heating for that hour, the outdoor temperature, because that's the source of the heat pump in this case, and also the required heat pump output temperature, which I just explained is the output of the emission system, depending on the energy needs or the external temperature. And then the heat pump performance is calculated, and as an output of that, fed into the energy need calculation for that hour is the energy that is available for heating, and the heat pump system energy use, and the COP, the performance of the heat pump system, and also optionally other details can be transferred from the one to the other. Well, we plan to perform a number of case studies, and the first case study is done on a single family house, which you see here. This is also the same case as described in the technical report corresponding to the 5216 part 1. And the variations are, calculations are done on an hourly basis, so we use the hourly calculation method. We selected 3 European climates, Oslo, Strasbourg, and Athens. For the heat pump, heating Athens is less interesting. Variation in energy needs, and for the heat pump system, we selected air-water heat pump system, so using external air. Inverter type, we have in mind to apply a variation in capacity and with or without an electric backup. And here a disclaimer, the spreadsheet that is used for these calculations is the most recent update, which is not yet available on the EPB Center website. It's currently under review. And this may also apply to the results I showed today, that these are preliminary results which will be reviewed in the coming period. So just as an illustration of a time series of the hourly heating needs in case of the connection with the heat pump, here you see the supplied heating for the last week in January, and you see the indoor temperature. And you, although at night the heating is switched off, you see that the temperature hardly decreases. So it's a heavyweight building, quite heavyweight building. And the outdoor temperature is around 0, and here a low peak -8 degrees, and no special things to see here. But if I go to the next slide, now I chose an undersized heat pump, and the heating needs which are covered by the heat pump are now much lower. And that is reflected in the indoor temperature. So despite the large mass of the building, you see the indoor temperature does not cannot be maintained at the required level at these low outdoor temperatures because the heat pump system is undersized. And here you see that in this case, the system for this week is quite undersized because these are the actual energy needs to maintain the set point temperature, and these are the needs that the system can apply. So this is a rather undersized system. And just to avoid a misunderstanding, if you look at these needs with an unlimited system, this is actually not the same as doing a full run of a calculation with an unlimited system size, because here the calculation of the energy need is influenced by the insufficient heat supply at the previous hour. So if you look at these runs, it's still a run with some moments and temperature which does not reach the comfort level as required. Then another example of a plot from the same calculations. So here you see the heating load duration curve for the month January again, and you see that the system runs for a small time at high load. Well, you could also compare it with the system capacity. Well, the nominal system capacity here is 7,000 watt, but in practice, depending on the conditions, it might be lower, of course, than that. But you see that it needs only a few percentage of the small percentage of the time. It needs these 6,000 watts, 5,000 watts, and so you would say with about 3,000 to 4,000 watt, it would be enough to cover most of the time the heating needs. So in this case, with the undersized system, we chose 3,000 watt as a nominal size, but the nominal size apparently is not enough here because at the large part of the time it runs at high capacity, and you've seen in the previous picture that the capacity is not enough to cover the needs. And other interesting pictures that can be shown are the performance of the heat pump systems, so the COP, for instance, as a function of the external air temperature, and that's quite relevant because the external air temperature is the source for the heat. External air is the source for the heat pump, and heat pump performance is very dependent on the source temperature, as you know. So you see here that indeed with low temperatures, the performance is decreasing quite rapidly. So it means also that it's quite relevant to take into account the interaction between the heat pump systems and the outdoor temperature to show this factor 2 difference in the COP. Here also at the high temperatures you see a drop in the performance. That's probably better explained in the next plot, because here you have the performance of the heat pump plotted against the heating needs, and you see here that the COP drops at the higher energy needs, and that's because the source temperature is increased. The source temperature is lower if you have higher energy needs. There are correlation between those two, of course. And here you see also a decrease at the low energy needs for heating. And that, of course, is because the system runs at a very low partial load, and whether these are really this dramatic drop or exaggerated, that is one of the things which has to be reviewed. Then for the undersized heat pump, a similar plot, the performance against the heating needs. So you see here a similar picture with somewhat less drop at a higher energy needs, probably due to the fact that it's undersized. So the conclusion is that one of the core standards for calculating the overall energy performance of buildings is EN-ISO 5216 Part 1, calculating the energy needs and indoor temperatures. There's a spreadsheet tool which is publicly available to perform the calculations according to this standard at the website. And now coupling to specific systems is being added, not for practical use, but just to demonstrate the impact of the interaction between the hourly energy needs and the conditions on one side and the system performance on the other side. This is work in progress, and what I showed now were first calculations, and this will be continued. Why are spreadsheets used? As I explained, because these are fully transparent. They allow you step-by-step validation and demonstration. They show all intermediate results and the references to the formula in the EPB standards. And as the downside of it, these are not for daily practice, but very important for the demonstration and validation. So this concludes my presentation. Thank you for your attention, and I love to give the floor to Gerhard Zweifel.
Yes, thank you very much. Welcome everybody also for my presentation, and good afternoon. I'm going to tell you something about a similar type of coupling as you just heard from Dick van Dijk, but rather than to a technical system, I coupled the thermal zone, the same thermal zone model according to EN-ISO 52000-1 to the natural ventilation calculation. My background is with Dick, and you have seen that already in an earlier webinar. I was part of webinar number 5, and you can read that later on if you want to know more about myself. So the standards that are involved in this coupling I'm talking about are the two, well, the first Dick has just talked about extensively, and the second one is this EN 16798-7 on calculation methods for the determination of airflow rates in buildings. It's available on the, I mean, there is a spreadsheet available on the EPB Center. But I also have to say it has been updated for the case study. I mean, for this example calculation I'm talking about. So at some time we will update also the content of the of the website of EPB Center. So why is it a sensible thing to couple these two spreadsheets? Well, on one hand, actually, the ventilation flow rate, according to EN ISO 52016-1, is defined as an input coming from another module. And this other module is this EN 16798-7. In the spreadsheet, the current spreadsheet, it's just using predefined values dependent on if it is run standalone, dependent on occupancy. And there is also in the current spreadsheet, there is a special ventilative cooling facility, but also operating on these predefined volume flow rates. So there is no actual calculation of the flow rates. This calculation in turn is done in this EN 16798-1 spreadsheet, according to the standard, of course. So the question actually that we can answer by this coupling is, does this flow rate that we assume really occur, or with a different formulation, what flow rates do really occur under certain circumstances, under certain conditions, such as climate conditions at a certain time step, such as internal temperature in the thermal zone at a certain time step. The contents of EN 16798-7, I have already a little bit talked about this standard in webinar 5. I repeat a couple of things, and I concentrate to the natural ventilation part, which is the majority of the standard, but it has also content in respect of mechanical ventilation. I'm not talking about that for the moment. This will be part of a later webinar, most probably. But for the moment, we stick to natural ventilation. So it has calculation methods for airflow rates through open windows, through vents, leakages, and passive and hybrid ducts. So all these elements are covered under certain boundary conditions, such as temperature difference, such as wind speed, depending on the type of ventilation that you have, such as single-sided ventilation, cross ventilation, stack effect over multi floors, more than one floor, so that these are all aspects that can be considered. And there are different levels of models in that standard, like a simplified, just single formula for an element, or detailed calculations, which actually involve iterations to resolve for a balance. So this is how I have already talked about. This is shown here at the side. So how is this coupling working? You now see a graph which is very similar to one of the graphs in Dick's presentation. From the building energy needs calculation for a certain time step, or calculation interval, actually, we should say, there is information actually transferred to the ventilation calculation, flow rate calculation. This is the outdoor temperature, wind speed, the indoor air temperature, and the indoor operative temperature. These are informations that are transferred. And then the calculation is done here, and as an information going back to the building energy needs calculation, there is the ventilation volume flow rate. In this coupling that I have performed here for this presentation, this is actually information taken from the previous time step. Time step is 1 hour. It's just taken from the previous hour, then calculated, and the ventilation flow rate is fed back to the next hour or current hour calculation. This avoids iteration actually, because otherwise we would have to iterate several times in here. What is also involved, which is not actually in any of these two standards, if you want, is a control signal. Actually, when should the window be opened or not? Actually, this is actually according to some sort of control scheme assumed. Maybe time dependent, it may be dependent on certain circumstances. And here, for the case study, actually, I only calculate the ventilation volume flow rate here with the simplified calculation method and only for open windows. Nothing else is taken into account in this example calculation. Again, it's the same example as Dick showed already for his example calculation with the heat pump. The climate is Strasbourg, and the ventilation type that was chosen is just, we assume that the east and west windows are openable on both floors of the building to a certain amount. So the type of ventilation is cross ventilation. And there are two regimes of operating the window opening. One is just for airing, just 3 times a day at 6 a.m., at 12 a.m. and at 6 p.m. The windows are opened for a certain amount. Actually, the window opening is defined as 15% of the total window area of these two orientations in the example. But here for the airing, we only do that for 30%. So it's actually 30% of the 15%, which can be assumed to be a limited time, not the full hour, but just 30% of that hour, which is resulting in, depending on the circumstances, is sometimes a little bit more, sometimes a little bit less than 1 air change just during these 3 hours. And then there is another regime added to it for ventilative cooling in summertime. So, and the circumstances are when the outdoor temperature is below the operative temperature in the zone, and when the operative temperature in the zone is above 24 degrees Celsius. Then the same opening is again applied, but the full hour, not 30%, full hour. And this is resulting in a maximum of about 5 air changes. It may be lower, we will see the results. The maximum that is reached during the summertime is about 5 air changes. But this is not, of course, something that can be changed, and a sensitivity study can be done about that, where you assume different opening percentages. So here, what we see here is some winter results, also for a selected week in January. You see the outdoor temperature and the wind speed. I plotted the wind speed as well here because it influences the flow rate as well. And the upper, so the upper graph actually shows a continuous ventilation, not the one that I just showed before on the slide before, but continuous ventilation, and the flow rate, which is actually this bright blue line here, because it's this scale, we can hardly see any any change of that. It's around 50-60 cubic meters per hour continuously. And then the other version down here is this airing 3 times daily that we can see, and here you can see the peaks in the flow rate. And the green line, you have already seen this type of course here in Dick's presentation. It's the energy need for heating in this case, with a peak in the morning because of the night setback, and then falling down and so forth. And here you can see actually 3 peaks because of this airing 3 times a day. So it really forces the heating to heat up to get to the set point of 20 degrees. And of course, this can be changed again. This could be done with different window openings and different times, etc. It's just one example. And then we have a week in summertime where on the upper plot there is only this airing 3 times a day, no ventilative cooling applied. It's a pretty hot week. Outdoor temperatures go up to 33 degrees peak on 3 days, 3 successive days here. But it's getting cooler later on here, as you can see. And it was cooler before, not shown here, but that can be. But there were also hot days already before, because otherwise the indoor temperature will not be as high as you can see here. So what you see here is just, again, these very small peaks. The scale is a bit different here, very small peaks of the flow rate from this airing and nothing else. The yellow line, by the way, is just the horizontal solar radiation, which doesn't really matter in this study so far. Then on the lower plot, actually, as opposed to the upper one, there is ventilative cooling applied, in addition to the 3 times daily airing. And what you can see is here actually an increased ventilation rate. But it goes up and down. It's not constant. It depends on the circumstances, especially on the temperature difference between indoor and outdoor air, and on the wind speed. These are the two driving forces actually for this flow rate. So here, yeah, this is just what I explained. This is the ventilative cooling flow rate here. Here we see some spots where the ventilative cooling is off because actually the indoor temperature, the operative temperature, which is the criterion, is below the set point. The set point is here at 24 degrees. So no ventilative cooling applied. It's only occurring when the temperature is above. But here, actually, the temperature is above the set point, but the ventilative cooling is set off again because the outdoor temperature is too high. It would heat rather than cool. So it is also set off here during this time. So this is actually a very short insight in this coupling of the thermal zone calculation and the natural ventilation calculation. So Dick has already talked about reasoning Y spreadsheets. They are fully transparent for step-by-step validation and demonstration. Now, this coupling that I was talking about brings in the information on the flow rates, depending on opening options, depending on climatic options, depending on control options. Other types of openings, such as the vent ducts, leakages, and so forth, could be added, or could replace actually the open windows. I just choose the open windows because this is the most straightforward way of doing that. The example calculation used only the simplified calculation. There would be the possibility to use detailed calculations, but this would raise calculation time because of the iteration that is involved. So at each time step, only this single calculation on the natural ventilation would iterate, and you would rather not do that with Excel. It can be implemented in some code, which is actually the intention, that spreadsheets are just showing that the standards, the formula and the standards are working. But actually the expectation is that people would write tools on the base of that. So this terminates my presentation. Thank you for your attention, and I give the floor to Laurent.
Okay, thank you, Gerhard, and good afternoon to everybody. So my task now will be to try to bring together all the pieces to get the calculation of the whole building. And of course, I will not be able to take into account all this interaction in such details, because of course it would be quite huge. So it will be a collection of, it will be with time a collection of reasonable calculation for the different parts and put together in a complete scheme. Well, about my background, you can read it later on the slides. And to start this work, I actually started from a different building, but then I will converge with the same example as Dick. It's you see here a single family house, 108 square meter floor area with floor heating, and we will analyze the difference between boiler and heat pump. There will be the availability of thermal solar with a storage of 300 liters and optional PV with 3 kilowatts and just a test with an optional battery of 5 kilowatt hours. And I only consider for now natural ventilation at a constant rate. So these two have, let's say, reasonable figures for a reasonable picture for an actual building. So we need all the pieces. So first of all, you need a climate. And for example, here it's generated by the reference years by the JRC Research Center of the Commission. And going through the EN ISO 52010 to generate the solar radiation on different planes and so on to get the climate data. And just to know where we are, here we have the result for Athens, Strasbourg, and Oslo. And here, what I choose is not far from the average climate of Strasbourg, with something more in the summer, because I wanted to have also some load on the cooling. Otherwise, this house probably would not have any load for cooling. We need use profiles, of course, and these are taken from 16798-1 for the single family house. So you can see the profiles for occupancy, for gains, and for lighting and all these kind of things. And now here we need, for example, a calculation. This is a result of the calculation of the indoor temperature and of the needs. And in here you have only heating needs, and you can recognize in this case it's continuous operation as it is in the default profile. And you see here the heating needs, we are decreasing. And when heating is not needed anymore, you can see the indoor temperature going in the free float mode. And here, from here to here, we have also some cooling needs because the set is at 25 degrees in this case. And then it goes back again to 20 degrees, just to have a full year. And if we go into some more details, here you can see again the heating needs, and here also some period of cooling needs in winter. Of course, that's just to say that we have such let's say a representative pattern during the year. Here we need also domestic hot water needs. This has been calculated with 12831-3. Actually, this standard gives you the daily needs, And here it's approximately 250 liters at 40 degrees, which makes sense for such a building. And we need also a profile to distribute this daily need along the day. And this is what was taken from the Excel profile, which is used for testing products, which looks more like what we could expect. So something in the morning, something in the evening, and maybe at midday, some other domestic hot water which is used. And this is the result. So these are the tabulated the values of the needs. These are the aggregated monthly values of the hourly needs, just to have a comparison. So you can see month by month, and you also have here the total yearly, and 59 and about 60 kilowatt hours per square meter per year. It means it is an average house. It's neither a very old with more than 100, nor maybe a much modern with something like 20, 30, like a passive house, which would be even lower. And you have also here the average domestic hot water needs, 15 kilowatt hours per square meter per year, and some cooling needs, just to know where we are in this house. So we are speaking about an average house, probably not old, not new, something in the middle with some insulation. And okay. Then we have to start some calculation. We can start with the pieces which are not interrelated with other systems or other things. For example, we can readily calculate which is the potential contribution of the thermal solar. So we can couple the standard about thermal solar with the standard about the storage. And you see the picture of 1 hour, for example. So we take into account, for example, you see depending on the temperature in the panel, which is on turn depending on the temperature in the storage. So if we have 70 degrees here and 70, it means that our storage probably is already very hot. This is the last charge in the evening in a sunny day, very probably. If we have a high temperature, even the bottom of the storage, it means it is filled. And you see that we estimate the losses and so the efficiency of this collector depending on the temperature in the lower part of the storage. And you get this kind of result to illustrate what happens. Here it is the solar in the orange. Here you see the solar radiation on your collector, and this in blue is what is going to which is going to the storage through the collector loop. And you can see here, for example, by chance here in the default climate, there is one day which is probably cloudy, so we have less contribution of our thermal solar system. As well as you can see here the dynamics in our, for example, storage. In this case, you see here this is a temperature in the lower part, and then so progressively up to the upper part. And you can see, for example, when the cold water is coming in, of course, you cool down, and then, for example, here you are heating up with the solar, and then when you get to the upper temperature, you are heating the whole of the thermal solar. So you can see really the dynamics, and you can estimate what is the contribution of the thermal solar. You can do something similar for the PV. So here again, it's the EN 15316-4-3, and depending on solar radiation, you have, of course, your PV output. And you see the same pattern. This is the same day where we had low, let's say, low solar radiation that we have seen before. So here you have the climatic data and the result. Sorry, this is really the electricity output. This also you can calculate independently, and then it will go into your balance. And so you can get this table, which is the potential contribution of renewable sources for this building, assuming that we'll use always a 3 kilowatt peak or this sizing, and we will turn it on or off and see what happens. And you see that the contribution of the thermal solar for domestic hot water is about something more than half and varying along the year. And here you have the potential electricity production. Here, this backup actually is the backup for the, it's not very clear. I should have a better line here. This is a backup for the required distribution input to the domestic hot water system. As you might notice, here I took into account losses of the domestic hot water distribution because this value is higher than the needs already. So in the calculation, it's taken into account in a simplified way. So that's a slide just to remember what's happening about other systems. They have been estimated for the moment by simple equations. So I take into account indeed auxiliary and losses of non-generation system. It means distribution emission, the temperature of distribution according to outdoor temperature. So a reset curve, because this has effect on the efficiency of the generators. So the boiler efficiency is depending on boiler water temperature. I use a constant second principal efficiency for heat pump. So I didn't yet took into account what Dick is experimenting now. It will be joined later, and it took into account indeed the air to water heat pump capacity is decreasing with outdoor temperature. So we have a reasonable replacement of some of the technical system to show the overall result, so the overall picture. And this is a calculation scheme which is indeed included in the it will be included in the revision of overarching standard. And you see here the needs, and each need, for example, heating is you have as the orange lines are something concerning heat. A little bit darker orange, this is the contribution of thermal solar, and here you have all the generators. In the middle we have system except generation, but particularly there's some attention of the domestic hot water store, because we have to satisfy domestic hot water needs, but you take into account that something is coming from your generators and something is coming from your thermal solar. And this is not yet activated. There's no simulation yet of the air handling unit. This will come later for this side. What you see in blue are all the contribution to auxiliary or to the main energy to all the generators. And with this calculation scheme, I can test the different combination, and later on I will connect the specific module. And here you see the complete balance, which is already done completely with a possibility for electricity, and depending on used and produced electricity, and you know how much you have to take from the grid or how much you have to export to the grid, and what you can store in the battery. This is a basic case with nothing special, no PV and no other things, so you are just taking the electricity from the grid. And as it was explained during the previous webinar, the first step in the calculation to have the situation under control, first you have heat extraction and electricity which are required to your generation devices. And then by selecting the generation devices, you might influence then your energy performance. In particularly, by selecting your generators, you can select if you will use electricity or any other energy carrier. And for example, heat can be generated by combustion, so you will go to a fuel, thermal solar, a heat pump. In that case, your heating will be based on electricity. You could have cogeneration, so again fuel, but here and you might take district heating. For the heat extraction, usually you will go to electric heat pump, but you could, so you turn this need for heat extraction in a need for electricity, but you could also go through an absorption heat pump. In that case, you will use fuel anyway. And for electricity, that's interesting that here you can also generate on-site renewable electricity. So once you decided your generators, you will come to two types of input: electricity, other fuels. With electricity, you may produce on-site from renewable sources. So we will test with and without the PV, and with a different value evaluation of the exported energy. When we have other fuels, your energy performance is bound to the property of the energy carrier. But indeed, this doesn't mean that it will be not always non-renewable. For example, you could use a biofuel on a boiler and you still have a renewable energy system. However, with electricity, it's far more common to be able to satisfy our needs, our building services with electricity. So we will see here some result and some comparison of the result with different configuration. You will have a series of tables where here you have the configuration. So the first starting point with the boiler with thermal solar, and if you remember, K exported is a parameter that tells you, it makes a decision if you take into account the energy performance of the building, if you are evaluating inside the exported energy. Of course, here we do not have anything to export, so it's quite straightforward. No exported energy, no influence. So we have a basic reference, which is our non-renewable primary energy performance. You have the result in absolute value and by square meter, which might be a more familiar figure for you. And you have also the amount of renewable primary energy. Here I didn't do the ratio because it's not very used commonly. Some countries also use a total primary energy, and you see the result here by square meter. You might have also the CO2 emission, and which could be interesting also. Here you have the idea of the cost. And as you see, with a reasonable assumption of the cost of the fuels, we have a little bit, we have 1,300 euros for heating and domestic hot water for this house. And of course, since there is no export, you're always paying for what you get. And this is true either for the primary energy, and you are always emitting CO2, and you are always paying a cost. And of course, so the renewable energy ratio, of course, in summer it's higher because we have the thermal solar contributing to domestic hot water, and here it's a little bit lower because we have the cooling going on the network, and on the average, of course, which is dominating, is the heating. So the first thing, we could add some PV, but of course, if you add some PV and you take K exported equals 0, so you don't take into account in the energy performance your photovoltaic which is exported, in that case, you will not change so much your energy performance. The previous value was 98, for example, and here, despite 3 kilowatts of PV, it's just 94. We are contributing for the cooling and for the auxiliary, and that's it. And the renewable energy ratio is still more or less the same. But here we can see what happens if you use, instead of an hourly calculation, the monthly calculation with the same input. So it's the same case, but instead of calculating with the hourly method, I calculate with the monthly. And you see the difference in the result. It was 94 kilowatt hour per square meters per year, and in that case is 90. It has changed. Why? That's because the monthly calculation cannot detect correctly when is the electricity produced and when it is used. So at any time we have energy production on site, electricity production on site, the hourly method will be the, let's say, nearly the only way to get a correct result. It's not a question of parameters of user input. It's question of how to deal with the calculated data. And the reason, of course, is this time mismatch. And despite, for example, one could say, okay, it's just auxiliary. I have such a high PV, so I should cover everything. But of course, PV is coming during the day, and maybe you have auxiliary or energy use during the night, and no chance to have this matching. Of course, you can make a turnaround, use a matching factor, but of course, this is not. And you see here the comparison in the electricity balance. In this case here, you have the electricity required for EPB uses. It means heating, cooling, ventilation, all these kind of things. This is the electricity produced on site, and of course, by monthly, you are producing always much more than required. And what is produced and used for EPB uses, and this is the difference, is exported to the grid. And if you take the hourly calculation, you still see that you need something from the grid. Instead, if you do this from the monthly, of course, you are covering everything, so no need to have something from the grid, and that makes the difference. Of course, here we are dealing just with auxiliaries, so it's not a big amount, but the same issue, much more important, you will see when we will deal with a system like heat pump. So you could use the K exported equal 1 is the same test of gas base. It's always a base case with our boiler, and we have introduced also the photovoltaic. In this case, we are including the exported energy into the energy performance. So you see that we have several months where the energy performance is negative, because we are exporting more energy than when we are using. And the same is true, you can understand this very well from the costs. In this case, I'm taking into account the fact that I'm selling energy. It's just the same as primary energy to the network. And you see that the energy performance is now what it was before, because we took into account. If we do this, in this case, the monthly method gave the same results, because it doesn't matter if you export or take energy from the grid at different times, because it's the same value in terms of non-renewable energy. But of course, if you have different weighting factor, so weighting factors are time dependent. And for example, for the cost is a weighting factor which typically could be time dependent for electricity, but you could imagine this also for the grid electricity. Depending on the time of the day, the mix of generator is not the same. So if you shift to some more detailed consideration, you need hourly method as well, even if the K exported equal 1. It's in a particular situation that the monthly is still working. This is again the same base case, but this time there's no photovoltaic. I just added a heat pump. And in this case, what we see is that again, the energy performance is nearly cut by half, from 98 to 51. And this is just because of the higher efficiency of the heat pump compared to the boiler, even taking into account the non-renewable primary energy conversion factors. So all the indicators show this, and probably the cost is not the same pattern, because of course it depends on the price of your electricity. Here we are buying everything from the network for the grid. And of course, if you add your PV, you say, okay, now I have a heat pump, I'm going full electric, and if I have a lot of PV, it should be fine. But of course, if you take into account, if you select K exported equals 0, it means exported energy is not taken into account. You are using not so much energy in winter when you need to run your heat pump, will produce a lot in summer when it's not used. So in that case, the advantage is not that much. Most of the electric energy is sold to the. You could, of course, have a turnaround. For example, instead of running continuously with a heat pump, so for example, running during the night in winter, you could try to run with an intermittent pattern to improve your performance. This you can show, for example, if you are on an hourly time calculation interval. Of course, if you go to K exported equal 1, you introduce the exported energy, and you see that in this case, the energy performance can become even negative, because you are exported more energy than you produced. And this is not surprising, this is normal. It means when you have this negative energy performance, it means that you, in principle, you have a positive energy building. Instead of nearly 0, it's even positive. But in that case, of course, you have to take into account into the performance what you exported. Of course, this you can reach these results, and it depends on how much you can produce. That's the reason for evaluating the potential of production of renewable energy. Because of course, if you have a multi-story building, an office with a lot of electricity used, in that case, probably you will not get up to such a result. Okay. And this is what just to underline this fact about these figures, and even the renewable energy ratio, which is higher than 1. That's normal. That's because we are producing more renewable energy than is needed for the building. And this is an example also what can happen if you take into account a battery. So in this case, of course, exported energy is discarded. But if you compare this with example 6, which was the PV, here it is, 14.4 kilowatt hour per square meter per year. And if this condition discard energy because it's not used at the right moment, you can then take into account if you have a battery and you see 31 in this case instead of 40, because the battery is capable of accumulating energy and giving it back when you need it. Here, so it's taken into account that the battery has an efficiency, has a maximum power when loading, has a maximum power when downloading, when using the energy. But indeed, you see here, for example, that in May, June, is covered by production, which was not without the battery. Then it is a question of sizing. If you want more of the electricity produced at the wrong moment, as always with all these. So these are just a couple of tables to have all the data at hand. This is a table where you see the variance, which has been numbered, the type of calculation hourly. You have the type of generator, boiler or heat pump. You have, is there any photovoltaic, any thermal solar, which is the selection for K exported, is there a battery, and here you have the performance results. And here this first table is all the cases with K exported equals 0. And you see here they are in red. When monthly, of course, you have deviations because of a calculation method. And you can have the full picture when you are using the K exported equals 0. So performance, of course, is better when going to a heat pump, and if you couple this with PV and potentially when you use a battery. In this case, I'm put into this table all the consistent evaluation when discarding the exported energy, so that you see exactly what is used by the building only for providing the EPB services. If you do all cases, in this case, I've removed the case with the monthly calculation just to see here in blue, you have the effect when you are, we change your K exported to 1, which is the most sensitive parameter in the 52,000. You get here to the negatives that we've seen. So this is just a table that allows you to get to a quick comparison. And so for now, the conclusion is, of course, as you that we have, if you go to realistic figures, you have some parameters, of course, on 52,000 that impact energy performance. And the most important choice is one you see here, and this was explained in the video. Of course, the starting point is the starting point is a good building envelope. Of course, it's a required good starting point, because then we have an amount of available renewable energy on site. Then the achievable performance range depends on the generation technology, and timing is more and more important. So you see that all these things can be completely described by this set of standards, and you can put the whole figure together to have the result for the whole building, and it's sensitive to all these parameters and also of some choices which depend on the regulation. And what is important is that the choice of parameters should be fully transparent for comparability, so that we are really comparing the energy performance calculated the same way, apart from even small details, but the biggest one is this K exported. So this concludes my presentation, and I think it's time for questions. Thank you for listening. Goodbye.
Thank you. So Q&A. Let's start with the first question. Do you have some examples of variable, so annually and monthly, energy efficiency ratio calculation for cooling system? Please feel free to answer this question. Anyone?
Is this to me? So for cooling systems, there's not yet any example as far as we proceed. We will of course proceed in that sense, but for now that's not.
May I give in addition some information? It's Gerhard Zweifel speaking. Well, we do not have performed any example calculations in the frame of our EPB center project, but on the EPB Center homepage where the spreadsheets are for all the standards. There is also an example, or two examples actually, three examples if I remember well, for cooling system calculations, which already involve coupled spreadsheets of all the cooling related standards. The point there is there is just an assumed profile of building use attached to that. There is no building model attached to that. So there is no link to the 52016-1 standard. But the whole system calculation is done in these coupled spreadsheets on the basis on an hourly basis, on the basis of an hourly pre-described profile taken from somewhere else, from some simulations or so. But that's available.
Thank you. Another question, what about the whole life cost to compare the various combinations in, for example, 20-year time? Can someone address this question?
Well, in these cases, we are dealing with mostly with operation costs. Of course, in the set of standards, there is one about economics, and in that case, you should have also your investment costs, the cost of materials, so you could do a full life cycle analysis. But for now, these calculations are meant to, what we are dealing in this project is dealing with the operation time. What happens at operation time?
Thank you. Let's move with another question. Why is the natural ventilation calculation not part of the building needs calculation?
Yes. Yes, I'm going to try and give an answer to that. Well, there are several points to that question. First is the main reason is that the standards and the spreadsheets attached to the standards are in this modular structure that Dick van Dijk has mentioned in his presentation. And these modules have been developed in different technical committees, so by different experts with different expertise, and then that's the main reason why it's not integrated. Which does not mean that in a tool that is supposed to be developed on the basis of all those standards, with the help of the spreadsheets to show how to implement, it would not be integrated in that case, because I mean, it is a tedious thing to couple these spreadsheets. And we do that to show that it works because they are separate, but actually in the final solution in a calculation tool would be that it would be integrated, of course. I hope this is an answer to that question.
Maybe Dick van Dijk speaking, I could add, I fully agree with what Gerhard says, but I could add that because we're dealing with standards, it's important that you have a transparent process and a fair process to review these draft standards and to approve the final versions of it. And if you have it all combined into one standard, then it would be very difficult to approve these standards, specifically because what Gerhard says, different expertises are involved, but also the process itself. If you would just have all these procedures together in one standard, it would be quite inefficient to try to get such a document agreed upon and published. And also for the maintenance of the documents in the revision phase, it will be quite difficult. So that's another important reason for having separate standards.
Thank you. So another question for you, Dick, I think. So how would you couple the heat pump calculation to the energy needs in case of a monthly calculation method?
Well, in case of a monthly calculation method, you have, of course, only monthly results on the energy needs for heating or cooling. So for the heat pump, the heating would be relevant. And then you need to find a performance value for the heat pump, which is representative for that month. The way you could do it is to look at the typical heating load distributions or typical outdoor temperature profiles and see for instance, how many hours do I have a certain outdoor temperature in a certain month, and then you could connect that to the performance of the heat pump for the same outdoor temperature. This is what's called the bin method. The drawback of this is that first of all, this could only be done in a generic way because you don't know the exact profiles of the hour. You know it for the external temperature, but you don't know it for the heating needs. And you cannot take into account the impact it has on the indoor conditions, which are strongly affected by the inertia of the building, and you cannot take into account the inertia of the building if you have only monthly results. So it would be a rough estimation and nothing more than that, and it would be quite generic, so applicable for to be applied for different buildings and different conditions without taking into account the specific conditions of a specific case. That concludes my answer.
Thank you. A question for Gerard, I think. Are the results from the natural ventilation calculations correct for short time airing? Should there not be a shorter calculation step used?
Well, yes, the question is justified in a sense because well, we have the results that I have shown, there was just for a full hour actually and window opening applied, whereas in practice you would maybe open the windows for 15 minutes or something like that. And of course, considering the dynamic effects, the building inertia and so forth, that this makes a difference. So there is a drawback in the like hourly calculation for such effects. It may be at the limit of the correctness of the results, I would say. But I have also to say, maybe Dick can assist me in that. Actually, the calculation method of the 52016-1 is not limited on the lower edge, not limited to 1 hour. It could be used with a shorter time step in principle.
Yeah, in principle, there's no difference, of course, in running it in shorter time steps. If you look at the current spreadsheet, that would not be simple to change it to a shorter time step just for practical reasons. For instance, climatic data are usually available on an hourly basis, so that would require interpolation. But interpolation is not the same as variation, so that it's not always becoming more accurate in that sense.
Thank you. Let's have another question, which I think is for Laurent. How do you think all this can be changed depending on climate and building type?
Well, the things that will change is mostly the ratio between electricity used and fuels at the level of carriers. You go to the overall result. And the type of buildings will, and the climate will change also your need for heat extraction, and electricity. So basically, if you are in a very cold climate and just residential, probably you are most influenced by the choice you will do for your heating. But you, of course, you can insulate well, you can use heat gains, so you can still come back to electricity via a heat pump. When it's other building categories, of course, other services can be more influencing. For ventilation, you need electricity basically, and if you need cooling, it will be mostly probably go through an electric chiller. And this is the first thing, shifting the balance towards more electricity if you have, let's say, a warmer climate typically, and non-residential uses which usually have more gains, so less need for heat. And also when you deal with offices, schools and so on, you have less need for domestic hot water, which you cannot reduce, for example, in other ways. And then, of course, if you move to electricity with reduced needs, you might profit of on-site generation to achieve a very good performance. And in this case, a limitation could be also the shape of your building. Multi-story, you just have some surface, you don't have an infinite power available, so it might be an issue for some categories which are a little bit more, in any case, energy intensive. And that's it.
Thank you. So if there are no more questions, I would stop the Q&A here. And I would like to thank our panelists and our audience. And I hope to see you for the next webinar of the series, which will be on the 8th of December. And you will be able to register very soon. Thank you again.